Today, we are going to talk about elastic potential energy. Previously, we discussed kinetic energy, which can be defined as the energy due to motion. We were able to calculate kinetic energy using the equation Ke equals 1/2 mv squared, where m is the mass of the object and v is the velocity at which it is moving. We also talked about gravitational potential energy, or the energy due to location, specifically height. We were able to calculate potential energy using the equation Pe equals mgh, where m is the mass of the object, g is gravity, and h is the height of the object above the zero. Now we can talk about elastic potential energy. Elastic potential energy is defined as a stretch or compression. So imagine a rubber band or a compressed spring. We saw in the overview of energy lesson that potential energy converts to kinetic energy when the forces are great enough to put an object into motion. So imagine we have a spring, and Bob applies a force to the spring. When Bob can no longer apply a force, the compressed spring will return to its original position, converting the potential energy into kinetic energy, sending Bob into motion. Just like with gravitational potential energy and kinetic energy, elastic potential energy can also be calculated using the equation Pe equals 1/2 kx squared, where k is the spring constant and x is the distance of the stretch or compression. Let's try an example. Imagine we have a spring that is stretched 0.1 meters and has a spring constant of 5.2 newtons per meter. We can calculate the potential energy using the equation Pe equals 1/2 kx squared, where k is 5.2 newtons per meter and x is 0.1 meters. Substituting into the equation Pe equals 1/2 kx squared, k equaling 5.2 newtons per meter, and x equaling 0.1 meters, we can calculate potential energy to be 0.026 newton meter, or 0.026 joules. As you can see, the unit for elastic potential energy is the same as for kinetic energy and gravitational potential energy. Joules are the standard unit for energy. To determine the force exerted by a spring, we use what is known as Hooke's law. The force a spring exerts on an object is directly proportional to the stretch of the spring and is in the direction opposite the stretch. This can be mathematically represented by the equation F equals negative kx, where again k is the spring constant and x is the stretch of the spring. Force in the equation is denoted as a capital F. Let's try an example. Imagine a spring with a spring constant 3.5 newtons per meter that is stretched 0.20 meter. Using the equation F equals negative kx, we can find the force exerted by the spring. Substituting the known values, we find the force to be 0.7 newtons. So how can we use this in lab? We will find spring constants. To find the spring constant of a spring, Hooke's law can be used. Measuring the stretch of a spring at a variety of forces and plotting the points, a linear relationship can be seen. According to the equation F equals negative kx, the spring constant k will be the slope of the line. This slope can be found using a computer application such as Excel, or by graphing by hand and finding the slope using 2 points. We will be attaching a mass hanger to a spring varying the mass and measuring the displacement or extension. It is important to measure from the exact same location on the spring each time for accurate results. Since we'll be graphing force versus displacement, we must recall some information. First, to determine the force, we must use the equation F equals mg, where g is 9.8 meters per second squared and m must be in kilograms. Additionally, some conversion factors must be known. 1,000 grams is equal to 1 kilogram, and 100 centimeters is equal to 1 meter. For this experiment, we must keep our units consistent. We must also consider safety concerns for this experiment. There will be no fire or dangerous moving parts involved. For this reason, you may wear any school-appropriate clothing for the lab. We will be using a variety of masks, though, and closed-toed shoes are recommended to prevent injury. If you come to class wearing closed-toed shoes, you will receive 5 extra bonus points for your lab worksheet. Thank you for watching, and be sure to show up to tomorrow with any questions you may have. Also, do not forget to wear your closed-toed shoes for 5 bonus points. Be sure to review before class.
created using Powtoon.